30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds.
I believe that this nation should commit itself.
12, 11, 10, 9. Ignition sequence start.
To achieving the goal
5,
before this decade is out.
2, 1. Liftoff. We have a liftoff.
Of landing a man on the moon and returning him safely to the Earth.
Liftoff, the clock's running.
On July 20th, 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first men to set foot upon the moon.
Houston, the Eagle has landed. That's one small step for man, one giant leap for mankind.
4 months later, Apollo 12 successfully landed on the lunar surface, and astronauts Peter Conrad and Al Bean walked on the moon November 19, 1969. And in April 1970, NASA launched the crew of Apollo 13 into the vast ocean of space to continue man's lunar exploration. But 56 hours into the mission, a devastating malfunction left the spacecraft leaking precious oxygen and the crew of 3 astronauts facing a life and death crisis.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
We could have lost O2 tank 2. We got to get a pressure readout on that thing.
O2 quantity number 2 is 0.
We are vetting something out into space.
Apollo 13's mission priority was no longer lunar exploration, but survival. With ground teams working around the clock, NASA faced the formidable task of returning the crew safely to the Earth.
Failure of the oxygen tank on Apollo 13 almost brought the mission to an end in a catastrophic way.
The mood in mission control was immediately one of disbelief.
I have absolutely no clue to what happened. Something happened to the fuel cells in the oxygen tank.
We're going to hit 100 psi in an hour and 54 minutes. That's the end right there.
So they only had a few minutes of power left.
We're still 70 to 80 hours away from the Earth.
We were running out of time to get the spacecraft back on course.
I don't think we should ever believe that rescue was inevitable here.
Without use of the lunar module, the mission was lost.
What do you think we got in the spacecraft that's good? It looks grim.
This 2-part film will tell the story of the men, the mission, and 13 remarkable factors that cemented Apollo 13's safe return to Earth as NASA's finest hour.
I'd say this is as serious a situation as we have ever had in manned spaceflight.
April 1970. NASA's Apollo space program is in full swing. The last 16 months have seen 12 men fly to the moon and 4 walk on its surface. For the crew of Apollo 13, preparations continue for NASA's most ambitious mission yet. Navy captain and veteran astronaut Jim Lovell is mission commander. Lovell is one of NASA's most experienced astronauts, and Apollo 13 will be his 4th spaceflight.
Well, I was among the second group of astronauts that came into the program back in 1962. My experience before consisted of basically naval aviation, mostly in the testing field. In NASA, I was assigned to 2 Gemini missions. Frank Borman and I were assigned to the Gemini 7 mission, and then Buzz Aldrin and I completed the Gemini program with Gemini 12. After that, I went into Apollo. I was a backup, actually, to Mike Collins. Mike had a neck injury, so I replaced him on Apollo 8. I then was a backup to Neil Armstrong on Apollo 11, and from there I worked back into Apollo 13, and that's where I am now.
The early astronauts who ranked for commander status in the early Apollo missions were test pilots who were very necessary for really getting hold of these beasts, putting reins on them, and wringing out the very best that they could in performance.
2 other former experimental test pilots will fly alongside Lovell on Apollo 13. Ken Mattingly assigned as Command Module Pilot, and Fred Hayes will fly as Lunar Module Pilot. For both Mattingly and Hayes, Apollo 13 will be their first flight in space. But just 7 days before the launch, the mission is already facing problems.
It all sort of started just before the flight. As we are approaching the final phase of our training, a turn of events occurred, and Ken Mattingly was exposed to the measles.
Ken Mattingly was the only member of the prime crew who didn't have immunity to measles.
At that time, we had to make a big decision. It was one which was not easy for me to help decide, and when they asked me what I wanted to do.
The flight surgeon's decision was that it was too big a risk to fly Mattingly on the mission, and therefore Mattingly was pulled from the Apollo 13 flight, and Jack Swaggart, the command module pilot on the backup team, was substituted.
The only apprehension that I have is that you work together as a crew. We did find that we did almost everything the same. And once this was determined, I had no apprehension at all. I felt that it was my job to get Jim and Fred there rested. I felt I could do that. I felt I could accomplish the majority of the orbital science objectives of the flight. I felt that we had a good mission and we could do it all.
Jack Swaggart will now fly as Command Module Pilot alongside Jim Lovell and Fred Hayes. Apollo 13 will be his first flight in space.
The main mission objective of Apollo 13 is basically the scientific exploration of the moon. We hope to find out a lot about the origin of the moon, and from that, the origin of our own planet, the Earth. We have, of course, a secondary objective in continuing the development and testing of the space systems itself for, of course, in future flights to other places.
Apollo 13 really went to take a step further than the previous two Apollos that had been on the moon. They had landed in areas called mare, these sort of flat plains, which occupy quite a bit of the moon's surface. And they contain no digging implements, really, so you only looked at the rocks that were right on the surface. And there's a lot of interest in really what's happening down below the surface of those mare. So Apollo 13's aim was to go to an impact crater where some huge collision had happened with an asteroid. That impact had thrown material out, and it sort of dug it up from lower regions of the crust. And Apollo 13 was targeted to an area called Fra Mauro, where there were uplands that had some of this material, this impact debris exposed. And that was really their main aim, to try and get to rocks that were characteristic of a different age of the moon compared to Apollo 12.
The particular objective of 13, of course, is a highland landing. We'll use the lunar module to land in a mountainous or hilly terrain called Fra Mauro, to explore Fra Mauro on foot, to look and find out exactly how it was formed, and also to deploy an experimental package called ALSEP.
It was a mission where the crew were definitely very interested in the science. The previous flights had been mainly engineering flights, Apollo 11 and Apollo 12, although a lot of science was done on both of them. We decided that we were going to have a heat flow experiment, which was going to measure any potential heat coming out of the moon, and that needed a drill, a Black & Decker 12-volt drill, specially developed to drill these 3-metre holes, 1 inch in diameter, on the lunar surface. It was a more sophisticated piece of equipment than flew on Apollo 12. Having the drill was a difficult thing to work on. They had to drill the 2 holes, they had to put probes down in them and have all this connected up to the central station. And it was the most complex experiment that we had up to that time. But 13's motto was from the moon knowledge, and the crew were really enthused with the science they were going to be doing and to do the best they could with our equipment. And we had a very good working relationship with them.
But the American public does not share NASA's enthusiasm for the next Apollo mission. With the Vietnam War raging on and US ground troops having faced fierce combat for over 5 years, public interest in the moon is fading fast. People believe Apollo 13 will just be another routine flight.
Public interest in the Apollo program reached a height in July 1969 when Neil Armstrong and Buzz Aldrin landed on the moon, but it rapidly decayed after that. There was some press coverage of Apollo 12, but by the time Apollo 13 flew, very little interest was shown. In fact, it was said that the TV companies, the broadcasters, were inundated with complaints from members of the public that their favorite programs were going to be bumped off schedule to cover Apollo 13.
It's interesting how quickly the public, and I guess we're talking mainly the American public, but worldwide as well, how quickly they sort of got a bit bored with it all, because it all seemed to go just like clockwork, didn't it? And people had got completely fed up with seeing the crew weightless and just poking at bits of equipment that nobody could understand.
I think one of the problems there was that NASA was not emphasising enough the science that was going on and the knowledge that was coming back. So interest was waning until the accident. And some people thought the accident was a stunt, just to get interest back again, but of course it wasn't.
For the eyes of the world now look into space, to the moon and to the planets beyond. And we have vowed that we shall not see it governed by a hostile flag of conquest, but by a banner of freedom and peace. We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge and understanding.
This is Apollo Saturn Launch Control. Now, as we move into the final phase of the countdown, we're receiving go, no-go checks from various elements of the launch team. The spacecraft test conductor gave the test supervisor a spacecraft ready. And the director of launch operations has given Apollo 13 a go for launch. T-minus 1 minute and counting. First stage, second stage, third stage going to internal power. T-minus 25 seconds and counting, and Apollo 13 is go. "17, guidance release. 15, 14, 13, 12, 11, 10, 9, 8. Ignition sequence has started. 6, 5, 4, 3, 2, 1. We have liftoff at 2:13. The Saturn V building up to 7.6 million pounds of thrust, and it has cleared the tower.
Houston, go at 30 seconds.
Roll complete and we're pitching.
Roger that.
You feel a Saturn V launch. It actually shakes you. You really are willing it to go.
Altitude 1.2 miles, velocity 1,500 feet per second. Stand by for mode 1, Charlie.
It's like millions of thunderclaps going off. All the simulations are done. All the rehearsing is done. Now it's time to get on with the job.
And 13, your go for staging.
Go for staging, Roger. We're EDS manual.
But 5.5 minutes into the mission, the crew feels unfamiliar vibrations during the second stage boost.
We confirm inboard out. Jim Lovell reports the inboard engine has shut down a bit early.
Suddenly, the central inboard engine shuts down 2 minutes ahead of schedule.
The early shutdown worried the crew, and they reported to the control center, something's happened, can you give us a reading on it?
Houston, what's the story on engine 5?
Jim, Houston, we don't have a story on why the inboard out was early, but the other engines are go and you're go.
Roger.
They were quickly reassured the other 4 engines were completely capable of getting them to orbit, so they knew within a few seconds of it happening that it wasn't going to affect the mission.
To Mission Control, the cause of the engine cutoff is a mystery, but it's a mystery that may have saved the entire mission.
During the ascent through the atmosphere, vibrations built up in the vehicle. In fact, these vibrations, known as pogo because of the way that the rocket vibrates along its axis like a pogo stick. These have been known since the beginning of flight of liquid-fueled rockets.
Pogo was a recurrent problem with the Saturn V's large engines, and could create such variation in their thrust that the vibrations could literally shake the vehicle apart. On Apollo 13, there were 3 instances of pogo vibration. The first 2 were similar to pogo that had been seen previously, but the third almost brought the mission to an end in a catastrophic way. The central engine of the second stage was vibrating vertically 16 times a second and severely flexing the Saturn V's framework.
So they had sensors in to detect when this was happening, and one of those sensors shut down the center of the cluster of 5 engines.
But had the vehicle gone through another cycle of growth of this pogo, it would have taken the vehicle outside of the structural limits, and that would have been catastrophic. And it's the Apollo 13 flight that galvanized the flight engineers to actually go back and revisit pogo, because it was obvious that the vehicle had been taken very close to failure and pogo suppression measures were put in place.
13 Houston, trajectory's good, thrust is good.
Roger.
And we don't have too much of a handle on why the inboard cut off early, except that it apparently was an engine problem, but we're certain that you'll be able to make TLI based on what we're looking at now.
Roger, nothing like an interesting launch.
That's right.
After the early engine cutoff, the flight continues as scheduled for the first 2 days. Apollo 13 is on course for the moon, looking to be the smoothest mission of the program so far.
Okay, you're on candid camera. We did notice one thing, Vance.
Right.
Can't comb your hair up here.
Well, I guess you have to give up something.
And I thought we'd get a picture of Jack, just so that all the girls know that he's still here.
Yeah, we appreciate that. There he is, Big Jack.
Apollo 13 presently at 177,861 nautical miles away.
"55 hours and 46 minutes into the mission, the crew finish a television broadcast showing how comfortably they live and work in zero gravity.
And now, for the benefit of the television viewers, Fred's engaged in his favorite pastime I found out on this flight so far.
He's not in the food locker, is he?
That's his second favorite pastime. He's rigging his hammock for sleep on the lunar surface now to try it out to see what it's going to be like.
Roger, sleeping and then eating.
It's kind of difficult here, Jack, getting into a hammock in 0G. I'm not sure if I keep floating away from it or it keeps moving away from me. We might give you a quick shot of our entertainment on board the spacecraft, which has been keeping us company for some time. This little tape recorder has been a big benefit to us in passing some of the time away in our transit out to the moon. And it's rather odd to see it floating like this in Odyssey while it's playing the scenes of 2001.
Okay, Jim, it's been a real good TV show. We think we ought to conclude it from here now. What do you think?
Roger, sounds good, and this is the crew of Apollo 13. Wishing everybody there a nice evening, and we're just about ready to close out our inspection of Aquarius and get back for a pleasant evening at Odyssey.
Houston. We've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks.
Okay. Stand by.
7 minutes after finishing the broadcast, Mission Control instructs Jack Swigert to turn on the fans inside the spacecraft's 2 liquid oxygen tanks, a routine procedure to stir the tank's contents. But as the fan inside the number 2 tank switches on, damaged wiring creates a spark.
The flight up until about 56 hours was, I guess what you'd call entirely nominal. We had followed the flight plan. We were ahead of the game.
Fueled by the oxygen, a fire spreads inside the tank. The rapid pressure buildup ruptures the oxygen tank.
Fred was still in the lunar module. Jack was back in the command module on the left-hand seat. And I was halfway in between in the lower equipment bay, wrestling with TV wires and a camera.
High-pressure gas floods the fuel cell bay in the service module, blowing out a 13-foot panel of the spacecraft.
When all 3 of us heard a rather large bang, just one bang.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Stand by, they got a problem. Okay. We got more than a problem.
Okay, listen, you guys. Fuel cells 1 and 3 are offline.
Right. That's what we're reading.
Flight engineers at Mission Control immediately respond to their instrumentation, which is indicating a major systems malfunction in the command service module.
Well, we're showing low N2 pressure on fuel cell 1. We're showing low O2 pressure on fuel cell 3.
That can't be.
Yeah, we might have lost fuel cell 1. And it looks like fuel cell 3 is gone. I can't believe that right off the bat.
2 of the spacecraft's 3 fuel cells appear to have been lost. These fuel cells are the prime source of electrical power in the command service module.
With the massive buildup of pressure from the cracked and split tank, there was a tremendous release of energy that not only blew the panel off, but shoved up the shelf on which the 3 fuel cells were sitting.
The shock closed a number of valves, and the fuel cells were running only on the oxygen that was in the lines from the valves down to the fuel cells. So they only had a few minutes of power left.
Fearing the spacecraft's hull may be damaged, Swigert rapidly attempts to seal the tunnel hatch between the command module and the lunar module.
The source of the bang not immediately determinable, and I was afraid that we might be vulnerable to losing pressure, so I proceeded to get the hatch in.
We're starting to button up the tunnel again.
5 times Swigert and Lovell try to lock the hatch in place, but the crew decides to stow the reluctant hatch and turn their attention to a new problem.
The oxygen pressure had gone in cryo tank 2, and the pressure in tank number 1 was rather slowly but steadily decreasing. It was obvious it wasn't holding its own.
We lost O2 tank 2 pressure.
We got to get a pressure readout on that thing.
O2 quantity number 2 is 0.
My concern was increasing all the time. It went from, I wonder what this is going to do to the landing, to I wonder if we can get back home again.
Looking out of the command module window, Jim Lovell sees gas venting from the service module into space.
It looks to me that we are venting something out into space. It's gas of some sort.
Roger, we copy your venting.
Not only is the number 2 tank completely empty, but the remaining oxygen stores in the number 1 tank are now leaking into the vacuum of space.
And when I looked up and saw both oxygen pressures, one absolutely 0 and the other one going down, it dawned on me, and I'm sure Jack and Fred about the same time, that we were indeed in serious trouble.
Although the command service module can operate on just 1 fuel cell, it requires an oxygen supply to generate power.
The force of that massive expansion of gas caused leakage to begin in the number 1 tank. There was insufficient pressure coming from that tank to keep the 3rd remaining fuel cell alive. Within 2 hours, the 3rd fuel cell had to be shut down.
It was quite apparent to me that it was just a question of time that the command module was going to be dead, that we were going to lose that fuel cell also.
That's the only means of electrical power for everything needed to get the crew back to Earth alive.
200,000 miles from Earth, astronauts Lovell, Hayes and Swigert are now flying towards the moon in a dying spacecraft. NASA must devise a plan to bring their men home before the remaining fuel cell fails completely.
Apollo Control, Houston, continuing to closely watching oxygen quantities, and if necessary, the 13 crew can use oxygen from the lunar module.
At the beginning of the Apollo program, NASA needed to develop a system that would successfully fly astronauts to the moon and back, and the decisions that were made will now directly influence Apollo 13's chances of survival.
At the very start of the program, when it was just drawings on bits of paper, there were a number of options, and various parts of NASA preferred various options. One option was to build a huge rocket, much bigger than Saturn V, it was called the Nova, and just send them straight to the moon, land the rocket on the moon, and then it was so big it had got fuel to come back. This was favoured, I think, by von Braun, actually. Then there was another scheme which had you go into Earth orbit, and then you separate out into various units, and some of them travel to the moon and some of them don't.
The system NASA committed to, known as Lunar Orbit Rendezvous, uses two separate specialized spacecraft, the Command Service Module and the Lunar Module, known as the LEM. The Command Service Module consists of two sections: the pressurized command module capsule that housed a crew of 3 astronauts and the equipment needed to fly to the moon and back, as well as survive reentry and splashdown, and the larger service module that provided propulsion, electrical power, and storage for the command module consumables, such as oxygen and water. The Lunar Module was designed to fly 2 astronauts down to the moon's surface, while the 3rd astronaut stayed in lunar orbit in the Command Service Module. Therefore, the Lunar Module had its own independent life support and power systems necessary to support the 2 men while they explored the moon. Within 3 hours of the tank rupture, all oxygen stores in the service module will be lost, along with all supplies of water, electricity and propulsion, and the command module will be unable to sustain life. But the benefits of the Lunar Orbit Rendezvous system are about to offer Apollo 13 a chance of survival.
Flight Econ.
Go ahead, Econ.
The pressure in O2 tank 1 is all the way down to 297. We're going to hit 100 psi in an hour and 54 minutes. That's the end right there.
We're starting to think about LEM Lifeboat.
Yeah, that's what we're thinking about too.
We figure we've got about 15 minutes worth of power left in the command module, so we want you to start getting over in the LEM and getting some power on that.
It was apparent, and the ground told us so, and they were right on the ball all the time, that the only way to survive the situation was to transfer to the lunar module, and we started going through procedures to get power on and to align the platform.
With its independent life support, power and guidance systems, the Lunar Module can act as a lifeboat and keep the crew alive.
The Lunar Module could act as a lifeboat because it's an independent spacecraft and was designed to go down to the lunar surface and come back, which meant it had a lot of capability, propulsion capability, life support and guidance. They were able to use all those functions as a backup to the failed systems in the command module.
The Lunar Module was the only vehicle available to get them out of a very tricky situation. Without use of the Lunar Module, the mission was lost. I mean, everything was lost.
Contingency plans to use the Lunar Module as a lifeboat had been drawn up by NASA earlier in the program, but now these plans and the spacecraft itself will be tested to the limit.
Gee, I think back in Apollo 9 we first started looking at the LEM as more or less a lifeboat, and fortunately, although the exact procedures do not tailor the exact case we've got, we had looked at the utilization of the LEM for an awfully long time, so we knew what the limitations were. We developed workaround procedures wherever it was possible. I think the LEM spacecraft's in excellent shape, and I think it's fully capable of getting the crew back. I think, as we have found before, every time we've put the LEM spacecraft to a test, it's always done much more than it was guaranteed to do, and I think this is a good case in point.
So a lot of thought had been given to the possibilities of rescuing the crew. Well, we didn't end up with a rescue capability. We didn't end up with a system that had duplicates. But we did have a system that could be turned on its end and used in a completely different way.
1 hour after the oxygen tank rupture, the dying systems in the command module have started draining power from the reentry batteries.
On Apollo, electricity was generated from fuel cells which use oxygen and hydrogen to react. And so the loss of oxygen in the service module meant that the spacecraft could no longer generate power, and the only power remaining was in batteries used for re-entry.
During a normal mission, the command module capsule was separated from the service module just prior to re-entering the Earth's atmosphere. But this separation severed its power supply from the onboard fuel cells in the service module.
So you have to have batteries in the command module to keep you going, and the re-entry batteries do that job. And without them, you can't operate the command module through re-entry.
We have 3 re-entry batteries in the command module, and we have no way of recharging these things now with the fuel cells gone, so we don't want to waste any of this valuable electrical power by running unnecessary equipment in the command module.
The command module must not run on the re-entry batteries any longer than necessary. Without these batteries, the crew will not survive the hazardous descent through the Earth's atmosphere. To minimize power consumption, Mission Control initiates emergency power down procedures.
We've really got to get that battery off the line.
Econ, I think we ought to start powering down.
Yeah. The emergency 1-5, power down.
Okay, 13, this is Houston. We'd like you to go to your checklist, emergency pages 1-5. Power down until you get an amperage of 10 amps, less than what you got now.
All non-essential systems in the command module are shut down except for the guidance computer, which holds the critical parameters needed to direct the spacecraft home. The crew must now race to power up the lunar module and transfer these guidance parameters to its onboard computer before they lose power in the command module.
It normally took 3 to 5 hours to power up a lunar module. They had to do it in 90 minutes.
They were really rushing to close down the command module and bring the lunar module up from cold.
They had to use modified lunar module power-up procedures, and these were developed very quickly between the crew and the ground, and they had to shortcut to get the lunar module up to keep them going.
We knew that the command module was going to lose it pretty soon because we were going to lose power. The first milestone was to get alignment on the LEM platform. Alignments are important because without knowing exactly which way the attitude of a spacecraft is in space, there's no way to tell how to burn or how to use the engines of that spacecraft to get the proper trajectory to come home. So we had to have an alignment on board the spacecraft.
A very important phase was when they were leaving the command module. The LEM attitude system didn't know where it was pointing.
Alignment of the guidance reference was normally done using stars. The problem after the incident was that there was debris floating around the spacecraft.
There was a whole bunch of particles like fireflies in a night sky. Jim Lovell was totally unable to get any sightings.
Fred and I went into the lunar module. Fred got the power on. We started to align the platform.
They needed to transfer guidance system knowledge of where things were pointing from the command module to the lunar module.
We used a procedure that was in the activation checklist. Jack gave us the angles.
And so they had to manually actually read the coordinates out and shout them into the LEM, and they were punched into the computer there.
I was so concerned about being sure that this arithmetic was correct that I had actually called down to the ground, let them do the math, came back in and put it in. But we did get a platform alignment, and that was our first milestone.
Once the guidance parameters are logged in their lunar module's navigation system, the command module is powered down to preserve precious re-entry batteries. With the lunar module acting as a lifeboat, NASA has stabilized the situation, and the crew have been bought some time.
My own personal involvement was that I was in the mission evaluation room. The mood in Mission Control was immediately one of disbelief. There was that sense that, okay, we've got a problem, it's the data. We see dropouts often. You see failed sensors giving erratic and spurious information. And then you begin to realize that there are a lot of things, and this is minutes, this is not hours. In minutes, you begin to realize there's a cascade of events which are tumbling, which means that they can only have one root cause. And the initial reaction was stabilization, to get the whole mission stable so that we could at least buy a bit of time.
If the situation remains stable as it is at the moment, there's no question but what we have the thing under control and we can return the crew safely to the Earth. Now, we're going to have to make some compromises in procedures as how you do that. But if everything remains as is, we can get them back successful.
But we were running out of time to get the spacecraft back on course. So rapidly there had to be, okay, there's no time for stroking our chins, wondering what's going on. Now's not the time to try and diagnose what the fault was. That will come later. Let's deal with the here and now, go forward, straight on.
We were trying to figure out what to do rather than to play out the old data.
And that's what we'll be doing till we get them back on the water, is concentrating on everything that is their lives are dependent upon at the moment rather than worrying about the accident, because there's nothing we can do about that now. The service module is no longer useful in most cases because the oxygen is depleted.
Essentially, assimilate as much data as possible, assign people to study those particular problem areas on how we keep the crew alive and how we keep our options open.
I was involved with the ALSAP experiment. I was a test engineer working at the Cape. We were called in the middle of the night telling us that it had happened. We went in and we had a discussion about whether we could use our nuclear power plant, which was on our experiments, on the ALSAP experiments, to give them extra power. They'd have to go outside, which would mean using a lot of oxygen because you'd have to depressurize and repressurize again. They'd be working with a hot 1500 degrees fuel capsule, manoeuvring that in 0G, getting it into the generator, and then finding a way of connecting that to the power system. And it was decided it was just too dangerous. They just would not succeed in doing it.
I worked as a support contractor to the Guidance and Control Division during Apollo. My impression during the early time of the mission was great concern for understanding what had happened and the best way to get out of the situation. And although there was a lot of tension among all the people, nobody really lost it. They somehow kept going and encouraged the crew. The crew, more than anybody, knew how serious the situation was. One gets the impression of a sort of calm. Searching for answers, but nobody really getting upset. And I think if anybody had really got upset, that probably would have been very serious.
NASA must now focus on the best strategy for returning Apollo 13 home. The free return trajectory was a flight path to the Moon designed by NASA earlier in the Apollo space program. Established by the Saturn V rocket, this trajectory would send the command service and lunar modules towards the Moon and use the gravity of the Moon to slingshot the spacecraft back to Earth without the need for further propulsion. The advantage of this trajectory is that in the event of a systems failure on board the spacecraft, the crew would still return safely home. However, as the Apollo space program progressed, the free return trajectory would restrict NASA from visiting more scientifically interesting landing sites. Therefore, a hybrid trajectory was flown from Apollo 12 onwards, where the spacecraft would maneuver away from the free return onto a specific translunar trajectory to reach their landing site. Prior to the oxygen tank failure, Apollo 13 had departed from the free return trajectory. But with its limited power and consumables, it is now vital that Apollo 13 maneuvers back onto the free return trajectory to make use of the Moon's gravity and slingshot back towards the Earth. Failure to get back on the free return will see the crew locked in lunar orbit, adding greater strain on the already limited consumables. But with the condition of the service module and its large propulsion engine uncertain, NASA is left with no option but to use the lunar module's smaller descent engine to fire the spacecraft back onto the free return trajectory.
We're going to make a free return maneuver of 16 feet per second at 37 minutes from now. That's a 16 foot per second dip burn in 37 minutes. Roger.
Many years before the first landing, one of the senior managers must have had a bad dream or something, because he said, what if that main engine that we need to get us back to Earth fails? It drops us into moon orbit, but we've no means of reigniting it. I want to know, he said, if the lunar module's propulsion system and its onboard consumables can be worked in such a way that it can get the crew out of moon orbit and on their way back to Earth. And those tests were done. And Grumman, the manufacturer of the lunar module, conducted tests to see how you'd steer the attitude of the two spacecraft from the other end, how you'd use the descent engine, normally used for going down to the surface of the moon, to boost you back out of moon orbit and back to Earth.
I had never tried that before. I really don't know who had, and it's a very difficult task. And we spent a lot of our first part of our emergency or survival time just learning how to control the spacecraft in this mode.
Almost every facet of the procedures that were used to get the crew back had been simulated in one way or another, but the really, really crucial thing which everybody feared was that nobody had put those all together in a string of events. It was always thought, well, this might happen, that might happen, one or the other, but never all in a row as they did on 13.
With time for the course correction running out, Mission Control and the crew work quickly to configure the lunar module for the free return burn.
Okay, here we go, the mid-course correction for free return. And I have your LEM GDA angles. Pitch, 5.86. Roll, 6.75. Your dip throttling, 5 seconds at 10%. Burn the rest at 40%. GDA angles, pitch, 5.86. Roll, 6.75. Dip throttle, 5 seconds at 10%. Burn the rest at 40%. Roger. Okay, Jack, we have a mid-course for free return. Okay, master arms on, 1 minute. Roger, Aquarius, you go for the burn. %. Okay, Aquarius, you're looking good. Okay, you're looking at 1685 now, Jack. That's affirmative, no trim required. Roger. Auto shutdown. Okay, Houston, burns complete. Roger.
With the successful firing of the lunar module's descent engine, Apollo 13 is once again on the free return trajectory back to Earth. But with only a 45-hour lifespan intended for a 2-man crew, the lunar module must now be configured to keep 3 men alive for over 90 hours.
Our feelings varied during the emergency. There were moments when I didn't know how much consumables we had, whether we could make it back or not, but in a situation like that, there's only one thing you can do. You just keep going, and you just keep thinking up where you can get more consumables. And so that's exactly what we did.
Well, the lunar module is not a big space. It's about the size of 1.5 telephone booths inside. To enable it to support 3 men for 3.5 days, the whole way in which it was operated had to change.
A big problem that faced them initially was what we call the consumables, so the oxygen, the electrical power, as it turns out the water, and then crucially towards the end the carbon dioxide. They had rather a small amount of electrical power in the command module, but they had oodles of it in the LEM, so they weren't really worried about lasting a couple of days in the LEM. Interestingly, they had a fair amount of oxygen to breathe in the LEM as well, and it's not difficult to understand why that was, because of course the LEM was planned to go down onto the lunar surface and open the door and let all the oxygen out, so they'd got plenty of oxygen to breathe in the LEM. Electrical power for the LEM was available, but the real crucial point was that they needed water to cool the electrical equipment. You can imagine all of these high-power things all jammed into this tiny space, so big problem with getting the heat out.
You can't cool electronics in space because vacuum doesn't conduct heat, so you don't get convection. So you need to cool them in an active way, so you run cooling water on cold plates, you put the electronics on cold plates. That's what we did on Spacelab. And you can keep things cool, stop them overheating and failing.
Mission Control estimates that the spacecraft will run out of water 5 hours before Earth re-entry, unless the crew restrict water usage as much as possible. All non-essential systems in the lunar module are powered down, and the crew reduce their water intake to a fifth of normal consumption, but suffer serious dehydration.
They powered down the lunar module as much as they could. I think it was only drawing about 20% of the power that it normally would, to reduce the cooling requirements. And I think they had about 4.5 or 5 hours of cooling water left by the time they got back to close to the Earth when they detached from the lunar module. But they had about 120 hours of oxygen because there was a lot of oxygen on the lunar module. They were not short of oxygen at all.
One of the great triumphs of the Apollo 13 rescue was the way in which the team managed to eke out those consumables and go from a situation where the consumables were predicted to be expended before the spacecraft got back, to a point where there was actually a little bit of slack in the consumable store by the time the vehicle returned to Earth.
But despite all of NASA's achievements in stabilizing the situation, one twist of fate remains undeniable. Had the oxygen tank ruptured at a different time during the mission, the astronauts would have been stranded in space with no hope of recovery.
There was a lot of fortunate incidents in 13 that would make it a completely unlucky flight. At the time it happened, I thought it was the worst possible time. Obviously, it was not the worst possible time for this particular incident to happen.
The oxygen tank failure occurred at a distance of about 200,000 miles from the Earth as the spacecraft was approaching the Moon. That is a quite fortuitous place for this to happen. Had the oxygen tank failure happened several hours before the point when it actually did, then the situation would have been very, very difficult. It's very likely that it would not have been possible to stretch the consumables out far enough so that the astronauts still had water and electrical power in time for re-entry. And without power for re-entry, the mission was doomed.
When you lose 2 fuel cells and an oxygen tank and the oxygen runs out of the other and all that, that's something very significant. It'd be very difficult to design against that. We're fortunate that we're on the way to the Moon with the LEM on board, or LEM attached.
If the explosion had happened before they had connected the lunar module round to the command module, then the astronauts couldn't have got into it, so there would have been no lifeboat.
Any time that you still have the lunar module in the condition that we have it in this case, where we've not used any of its consumables, then we're in a very good situation. We've always called the LEM a good lifeboat under those circumstances. If at any time in the mission, however, the LEM had separated, then it would be a fatal situation.
Had the event happened later, after the lunar module had separated from the command module, after the point where the 2 astronauts bound for the lunar surface had actually detached and were on their way down, or even on the surface, then the situation would have been very serious because of the fact that the command service module would have been left without any power, so communications with the astronauts on the surface would have been nigh impossible.
You'd have had a dreadful, dreadful situation where the guy going around the Moon was lost, and the 2 guys on the Moon for a while were okay, but then there was no way back for them. So if you're looking for good luck in the Apollo 13 story, it was that it happened when they could rescue them. There were a lot of opportunities before that and after that. If it had happened then, they couldn't have rescued them. So I don't think we should ever believe that rescue was inevitable here. And a lot of the NASA engineers, although publicly they were saying, well, you know, this is fine, their estimate of the chances were below 50-50, and some a lot less than that.
If you're going to have a catastrophic failure of an oxygen tank on a flight to the Moon, then somewhere around about 200,000 miles from the Earth outbound is possibly the best place to have it.
Apollo 13 now 421 nautical miles above the Moon. Just a little over 1 minute now from time of loss of signal with the spacecraft. Standing by, continuing to monitor. This is Apollo Control, Houston.
we're still something like 70 to 80 hours away from the Earth. I would only guess that the crew feels that the situation is under control, but they were in a serious condition and they knew they had a job to do. If the situation remains stable as it is at the moment, we have the thing under control and we can return the crew safely to the Earth.
With the spacecraft back on course, the consumables stable, and the astronauts surviving in the lunar module, NASA has successfully averted the immediate danger. But with Earth still 250,000 miles away, the return flight is about to present the crew with a whole new series of life-threatening situations.
This is Apollo Control, Houston. We've had loss of signal with Apollo 13 as it passes above the backside of the moon. We're at 77 hours, 9 minutes, now into the flight of Apollo 13.
Next time in Part 2.
Carbon dioxide levels in the lunar module are rising.
There was no way that the astronauts would survive.
What have we got up there? What can we put together to overcome this problem?
The main heat shield was not designed to operate in free space for extended periods of time.
The crew were beginning to suffer.
The spacecraft kept going down in temperature and I was freezing.
It was a dire state. It was a real emergency situation.
30 seconds and counting. Astronauts report it feels good. T-minus 25 seconds.
I believe that this nation should commit itself
12, 11, 10, 9. Ignition sequence start.
to achieving the goal
5,
before this decade is out
2, 1. Liftoff. We have a liftoff.
of landing a man on the moon and returning him safely to the Earth.
Liftoff, the clock's running.
On July 20th, 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first men to set foot upon the moon.
Houston, the Eagle has landed. That's one small step for man, one giant leap for mankind.
4 months later, Apollo 12 successfully landed on the lunar surface, and astronauts Peter Conrad and Al Bean walked on the moon November 19th, 1969. And in April 1970, NASA launched the crew of Apollo 13 into the vast ocean of space to continue man's lunar exploration. But 56 hours into the mission, a devastating malfunction left the spacecraft leaking precious oxygen and the crew of 3 astronauts facing a life and death crisis.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
We could have lost O2 tank 2. We got to get a pressure readout on that thing.
O2 quantity number 2 is 0.
We are vetting something out into space.
Apollo 13's mission priority was no longer lunar exploration, but survival. With ground teams working around the clock, NASA faced the formidable task of returning the crew safely to the Earth.
Failure of the oxygen tank on Apollo 13 almost brought the mission to an end in a catastrophic way.
The mood in mission control was immediately one of disbelief.
I have absolutely no clue to what happened. Something happened to the fuel cells in the oxygen tank.
We're going to hit 100 psi in an hour and 54 minutes. That's the end right there.
So they only had a few minutes of power left.
We're still 70 to 80 hours away from the Earth.
We were running out of time to get the spacecraft back on course.
I don't think we should ever believe that rescue was inevitable here.
Without use of the lunar module, the mission was lost.
What do you think we got in the spacecraft that's good? It looks grim.
This 2-part film will tell the story of the men, the mission, and 13 remarkable factors that cemented Apollo 13's safe return to Earth as NASA's finest hour.
I'd say this is as serious a situation as we have ever had in manned spaceflight.
Previously in Part 1.
When I looked up and saw both oxygen pressures, one absolutely 0 and the other one going down, it dawned on me that we were indeed in serious trouble.
After a ruptured oxygen tank cripples the Apollo 13 spacecraft, Mission Control and the astronauts immediately follow emergency procedures.
The only way to survive the situation was to transfer to the lunar module.
The lunar module could act as a lifeboat because it's an independent spacecraft. They were able to use it as a backup to the failed systems in the command module.
It normally took 5 hours to power up a lunar module. They had to do it in 90 minutes.
Without knowing exactly which way the spacecraft is in space, there's no way to get back home again.
Alignment was normally done using stars. The problem after the incident was that there was debris floating around the spacecraft.
The lunar module's descent engine is fired to put the spacecraft on a return trajectory back to Earth.
Okay, Aquarius, you're looking good. Okay, Houston, burn complete.
NASA works to reconfigure the two-man lunar module to keep 3 men alive for over 90 hours.
One of the great triumphs of the Apollo 13 rescue was the way in which the team managed to eke out the consumable store.
In a situation like that, there's only one thing you can do. You just keep going, and you just keep thinking up where you can get more consumables.
We've had loss of signal with Apollo 13 as it passes above the backside of the moon. We're at 77 hours, 9 minutes, standing by, continuing to monitor. This is Apollo Control, Houston. Apollo Control, Houston, we're coming up now on 1 minute from time of reacquiring Apollo 13. Standing by now for acquisition.
Aquarius, Houston, over. Aquarius, Houston, over. Apollo 13, Houston.
Go ahead, Houston.
Hey, you're loud and clear now.
Roger.
With the lunar module acting as a lifeboat and the spacecraft back on the free return trajectory, Apollo 13 is on course to splash down in the Indian Ocean in 4 days' time. But with no recovery forces deployed in the Indian Ocean, the crew would be left floating in the command module, waiting for rescue. Mission Control must reduce the flight time to have splashdown in the Pacific Ocean, where naval recovery forces are already in waiting.
Our first milestone was to get us back on free return. The second one was to get us home early. The flight time back home was 155 hours if we had done nothing else. But the ground had decided to burn at about 2 hours past the moon, at about 79 hours, a maneuver to shorten the time to get home again.
Not only will a shorter flight time put less strain on the consumables, but it will also ensure the capsule re-enters the Earth's atmosphere above the Pacific Ocean. The team at Mission Control have 2 burn options. Both will require the use of the lunar module's descent engine. The first will speed up the flight by 36 hours. Although the fastest of the 2 options, this burn will require jettisoning the service module, something NASA is reluctant to do.
That would expose the heat shield of the command module to very high and very low temperatures, and they were very concerned about cracking that. I mean, that heat shield was absolutely the lifeline. You couldn't re-enter the Earth's atmosphere if that wasn't in a good condition.
The main heat shield, of course, was not designed to operate in free space for extended periods of time. It's designed for re-entering the Earth. And there was some concern if you jettisoned the service module that you'd cold soak that heat shield and get problems, so for that reason they preferred to keep the service module on.
Nobody knew if the command module could survive that thermal condition, super cold temperatures of space, coming back all the way without the service module attached.
And in addition, the burn will require all remaining fuel for the engine, posing yet another problem.
Further corrections to the spacecraft trajectory that may be necessary as the spacecraft approached Earth would no longer be possible.
With this in mind, NASA chooses the safer second option, a shorter 4-minute burn that will return the crew only 12 hours sooner, but will preserve fuel for later course corrections.
Given the success that the mission operations team were having in stretching out the amount of time that the consumables would last, there was no necessity to go for these very extreme options, and they could afford, therefore, to take the lower energy approach, leave some fuel in reserve, keep the heat shield safe, and come back at about launch plus 142 hours.
It was mainly a question of what is the safest way to do this. And all the decisions that were made turned out to be exactly right, because they came back almost the slowest routes you could from the moon, because they wanted to retain the possibility of making some small corrections between the moon and getting back to the Earth, so that they came in just the right height in the atmosphere. And as they approached the Earth, actually, they started drifting away, and they were quite anxious about that. So having preserved some fuel in the LEM motor for doing these corrections was exactly the right decision, because they actually needed to make those corrections on their way to Earth. It would have been horrifying if they'd, saved the astronauts only to see them zoom past the Earth, by a few miles, or crunch into the atmosphere and get burnt up, both of which were possibilities.
The precision of this burn is so critical that the flight dynamics team at Mission Control insist that the lunar module's guidance computer be used to control the spacecraft. But as this system drains a lot of power, it will have to be permanently shut down once the burn is complete. From then on, the astronauts will be flying manually.
The descent propulsion system burn duration 4 minutes 24 seconds. Flight Director Gene Kranz now going around the room for a go-no-go status from each member of his team.
Aquarius, Houston, over.
Go ahead, Houston.
Jim, you are go for the burn. Go for the burn.
Roger, understand. Go for the burn.
Less than 30 seconds away from scheduled time of ignition on our Paracynthian plus 2-hour burn for the Apollo 13. The engine is armed, standing by.
We're burning 40%.
Aquarius, Houston, you're looking good.
Roger.
Go with 2 minutes.
2 minutes, Roger.
Go with 3 minutes. 10 seconds to go.
Shut down.
Roger, shut down. I say that was a good burn.
Roger. So now we want to power down as soon as possible.
Commander Jim Lovell reporting shutdown. The engine is off. Apollo 13 now 5,426 nautical miles out from the moon. We're at 79 hours, 32 minutes into the flight.
Almost exactly 24 hours after the oxygen tank rupture, the crew complete the burn. Apollo 13 will now arrive back at Earth for a splashdown in the Pacific. But in order to preserve consumables, every system in the lunar module is once again powered down, except for the guidance, communications, and water cooling systems.
The ground was very much concerned with power, and we were too. And we decided to go into a power down mode. We turned off just about everything.
I guess everybody, myself included, got a little bit fooled about how low the LEM actually could get down to, and after completing this power down, it settled down on consuming about 11 amps an hour.
The lunar module, one of the most sophisticated machines ever built, is now running on less power than a household vacuum cleaner.
This is Apollo Control at 82 hours, 30 minutes. The lunar module has been powered down on board the spacecraft. All 3 crewmen are scheduled to be eating at this time.
In a strange way, the uniqueness of Apollo 13 came to our aid again, because this was the first mission to carry actually a level of wet pack food. So being unable to use drinking water because water was so scarce, they could actually suck moisture out of the wet pack foods to get water and electrolytes, which the body desperately needs in order to maintain the mental faculties. And mental faculties were needed pretty sharp for the crew under those appalling conditions.
With Apollo 13 speeding back towards the Earth, the crew can at last afford to catch up on some much-needed sleep.
Of course, in the early periods of this particular flight, we didn't want to sleep too much. We were sort of worried of what was going to go on. But I went into the command module one time to go to sleep, and Jack was on top of the couch, and I said, "Jack, put up all the window shades. Let's get the place nice and dark. We'll just relax and have it nice and dark in here. We can really get some sleep." And I woke up a couple hours later, and I was freezing. As normally happens, putting up window shades in space cuts out the sunlight and normally cools down the spacecraft, but in most flights, the heat from the systems will quickly re-warm it. And as soon as we get the window shades up, you'll be in normal position again. But we got the window shades off after that, and the spacecraft never did warm up again. Command module just slowly kept going down in temperature until I think just prior to reentry, down to about 38 degrees.
With no power for the electric heating, temperatures inside the spacecraft drop to almost freezing point.
How does it feel, Jack?
I tell you, it gets cold. I don't know whether we'll be able to sleep tonight. It must be about 35 or 40 degrees. And they both came down here rubbing their hands, shivering. It's pretty cool upstairs.
Right, that's what I was worried about.
The command module, which was dead, completely switched off, completely lifeless, was cold. There was ice forming on the inside of the windows. The crew were beginning to suffer because of that environment.
We became concerned about keeping warm, and Fred and I broke out our lunar boots, which we had stowed away in the lunar module, and Jack looked at his wet feet a couple times. But he had an extra set of underwear, so he put that on.
They were so cold, they were not even able to sleep properly. And in restricting their water intake, I think Fred Hayes had a urinary problem as a consequence, and he was in pain for quite a lot of time on the way back.
It was sort of a chilling coldness. The walls were perspiring, the windows were completely wet, and it wasn't too healthy. I recall that we went in there to get some hot dogs one day, and it was like reaching into the freezer for the food.
It was a dire state. It was a real emergency situation.
The dropping temperatures not only pose a threat to the astronauts, but to vital equipment on board the spacecraft, which can be damaged by the extreme cold.
In normal flight, the command service module would maintain reasonably steady temperatures. So you design things generally to work about 20 degrees centigrade, normal temperature. And you don't want things going too far away from that.
With the crew and the success of the mission dependent on this precision equipment, it is essential that Mission Control keep the spacecraft within the acceptable thermal conditions.
The people here in Mission Control Center are looking at ways of setting up passive thermal control for thermal balance for the spacecraft during the remainder of the coasting flight.
As well as facing the freezing temperatures of deep space, one side of the spacecraft is constantly baked by the extreme heat of the sun.
In Earth orbit, of course, low Earth orbit at least, half the time you're in sunlight, half the time you're in darkness. On the way to the moon, the sun's there all the time. So you don't want one side of the spacecraft getting hot and the other side getting very cold.
Mission Control instructs the crew to initiate passive thermal control, a maneuver that slowly rotates the spacecraft to evenly distribute the sun's intense heat.
Okay, Jim, in order to maintain even heating, we just have to yaw the whole machine about 90 degrees.
Okay, we have to yaw the machine and take them at the 90 degrees.
That's affirmed.
So they use passive thermal control barbecue mode, which is rotating the thing about three rotations an hour to stabilize the temperature. And it also sort of controls the attitude of the thing, a bit like a rifle bullet, so it doesn't drift off too much.
This passive thermal control procedure had been used on other Apollo missions to ensure the spacecraft was kept at an optimum operating temperature. But for Apollo 13, the maneuver has the added bonus of warming the crew in the near-freezing lunar module.
They modified the angle of the spacecraft so that the sun would warm up. They warmed them up through the windows, basically.
Mission Control and the crew have been successful in establishing passive thermal control, but there is little time for celebration. Ground teams must now turn their attention to a new problem looming on board the spacecraft.
When you breathe oxygen, you exhale carbon dioxide. And that carbon dioxide, if you don't do anything about it, builds up in the sealed environment of the space capsule and becomes a poison. And so, left unchecked, the carbon dioxide concentration goes up, the astronauts feel sleepier and sleepier, and eventually they go to sleep and never wake up.
However, all of the Apollo spacecraft have systems that can remove carbon dioxide from the air in a process known as scrubbing.
You blow the air through crystals of something called lithium hydroxide, and there's a chemical reaction, and it captures into a solid form the carbon dioxide, takes it out of the air, and then you get fresh air coming out the other side. The command module had a scrubbing system, so did the lunar module, but the lunar module was designed to carry 2 men for 2 days, whereas now it had to carry 3 men for 4 days. So that's 3 times longer, 3 times more carbon dioxide being exhaled by these men.
With this additional carbon dioxide, the scrubbing canisters in the lunar module are being overwhelmed. However, the command module has plenty of unused canisters. But with the command module powered down, its scrubbing systems are not operational.
It wasn't possible to take the lithium hydroxide crystals from the command module and place them in the lunar module because the shapes were different.
Because 2 manufacturers had bid and competed for these 2 separate spacecraft, and they each built their own design of lithium hydroxide canister.
The command module canisters of lithium hydroxide were square cross-section, and believe it or not, the ones in the LEM were round cross-section. So you couldn't take a canister from the command module and just plug it into the slot in the LEM.
So the problem that the mission controllers faced and the astronauts faced was how to make a square peg fit a round hole.
This was a very serious problem. I mean, it could easily have been the end of the rescue mission had they not solved it.
NASA engineers must rapidly devise a system that converts the square command module canisters for use in the lunar module before the carbon dioxide reaches dangerous levels.
Okay, just some info. We're working up a procedure for you to use command module LiOH canisters in the LEM so that you can continue scrubbing the LEM atmosphere. So sometime in the future we'll be coming up to you with that procedure.
A group of life support engineers at NASA knew immediately after the oxygen tank rupture that if the lunar module was used as a lifeboat, then carbon dioxide poisoning was going to be a problem. They also knew the astronauts would somehow need to patch command module canisters into the lunar module's life support system if the crew were to make it home alive. The responsibility fell on this team of engineers to construct a canister adapter using only equipment available to the astronauts on board the spacecraft before CO2 levels get dangerously high.
The guys said, okay, lay out on the table what we've got, and let's get a lunar module canister and a command module canister. How do we bring these together?
Here again, I think we must pay credit to NASA for its incredibly philosophically intelligent way of organizing missions. Everything that went on the spacecraft went onto an inventory. So the people on the ground knew everything that was on the spacecraft, and that gave them the opportunity to sort of assemble all of this in their minds and say, hey, what have we got up there? What can we actually put together to overcome this problem?
Within hours, the team have created an adapter using spacesuit hoses, plastic bags, and cardboard flight plans. But holding all of these components together to create the vital airtight seal is one of NASA's secret weapons.
Duct tape. We couldn't have gone to the moon without duct tape, and we certainly wouldn't have got the Apollo 13 crew back without duct tape. It was very, very useful.
If you're in a weightless environment and you want to stop your pencil kind of just wandering off into somewhere else, you stick it to the wall with a piece of duct tape. You're forever sticking up lists of instructions or lists of things to do or pieces of equipment to the walls with duct tape. And clever minds might think of a way of getting around it if you didn't have duct tape, but it was the obvious thing to use, and luckily they had some there. But I use the word luckily, it was because it was a useful thing to have, and they had it on board.
This is the scavenging hose, the exhaust hose, if you will, from the suit. And we just put the lithium hydroxide canister on the end of it, and it's not so easy to fasten on there.
They placed the rectangular lithium hydroxide canister inside the plastic bag with a hole in front of the astronaut's spacesuit pipe that then allowed air to be pushed through that lithium hydroxide canister.
We've used a data card out of the flight plan to make a structure so that the plastic cover here won't collapse on the end of the hose.
And they then found a way of connecting at the other end of the spacesuit hose to a spent lithium hydroxide canister already fitted in the lunar module.
And we've had one of these running for about 3 hours over in the 11-foot chamber in Crew Systems, and all indications are that it's doing the job.
So it literally was cobbled together on a desktop. It sounds Heath Robinson, but in fact it was just make, do and mend. And that's often the best way for solutions.
Mission Control's final hurdle is creating a clear procedure for the tired and cold astronauts to follow to correctly assemble the canister adapter.
We wish we could send you a kit, and it'd be kind of like putting a model airplane together or something. As it turns out, this contraption will look like a mailbox when you get it all put together.
The ground read us up a procedure in order to adapt some of the command module lithium hydroxide canisters for use in the LEM. And as they read this thing up, Jim and I constructed one of these things.
Cut a piece of tape this long, put it up there, do this, do that. So the guys in the LEM actually replicated this, and it worked a treat. Within an hour of switching it on, the carbon dioxide levels were way down, and they were through that really serious consumable problem.
So these were very effective devices, and we used 4 of these command module canisters and never did use the main canister that we had in reserve for the LEM.
We're now showing 0.1 partial pressure of carbon dioxide in the lunar module. So apparently the engineering using the command module lithium hydroxide canisters and the plastic bag and the suit hoses is working out all right. And at 96 hours, 3 minutes ground elapsed time, this is Apollo Control, standing by.
Having avoided carbon dioxide poisoning, the crew can breathe easy. But concerns are now growing at Mission Control about the spacecraft's trajectory. The flight dynamics team tracking Apollo 13 can see it drifting off course. Although this drift is small, its impact on the capsule's re-entry into the Earth's atmosphere could be disastrous.
You are looking to enter the Earth's atmosphere around the side of this great big sphere at an angle of between just 5.5 and 7.5 degrees, coming all the way back from the moon. So the precision with which you align the flight path is crucial to keeping the crew alive.
If Apollo 13 stays on this drifting flight path, its re-entry angle will be too shallow, and the capsule will skim off the Earth's atmosphere, stranding the crew in space. The astronauts must once again perform a precision burn of the lunar module's descent propulsion system and trim their flight path, steepening the capsule's re-entry angle, ensuring it is captured by the Earth's atmosphere. But if the burn is not accurate and the angle is made too steep, the heat shield on the capsule will fail and the crew will burn up during re-entry. The astronauts' lives now depend on the accuracy of this maneuver, but with no power to run the lunar module's primary guidance computer, it was shut down after the last acceleration burn. Mission Control now need a method to precisely align the spacecraft to have any chance of correcting the re-entry angle.
The procedure for putting the spacecraft in the proper attitude would be to use the Sun and the Earth as reference points. This, of course, would be a backup procedure. The normal procedure would be to use the onboard guidance equipment, and only in the event of some unforeseen failure would this backup procedure be used.
With no power available for the lunar module's primary guidance system, the crew must use the secondary abort guidance system, which consumes less power. This system will help the crew position the spacecraft for an accurate burn, but must first be calibrated to be of any use. The technique that must now be used has only ever been trialled once before, by only one astronaut, Jim Lovell.
On Apollo 8, we were concerned with perhaps losing a platform on the return voyage home, and since no one had ever made a lunar trip before, we were looking at sort of ways of determining how we could make these corrections home. And some of our people here at MSC had come up with an idea about using the terminator of the Earth to orient the spacecraft and then the sun position to get orientation and pitch. And with that knowledge, we could then make corrections to correct our angle of entry into the atmosphere.
This backup procedure uses the Earth's terminator as a target. The terminator line is the separation between the illuminated day side and dark night side of the planet. The terminator provides a fixed target on the Earth and can be used to establish an accurate alignment.
And the way that they did this was to use the Crewman Optical Alignment System, or COAS. And by maneuvering the spacecraft so that the COAS had the Earth's terminator aligned with the site, it was possible to create the correct geometry for the burn to take place in the right direction.
So at 105 hours, they gave us instructions to relight the descent engine, to orient the spacecraft in this manner, and give this particular procedure a try. And when they read up the procedure to us, I just couldn't believe it, because even on Apollo 8, I thought I'd never in all the world have to use something way out as this. And here I was on Apollo 13 using this very same procedure that was developed some time ago.
Okay, Jim, now basically if you put the horizontal line on the COAS on the horns of the Earth, that will put us in burn attitude.
Okay, I think I have a handle on the attitude, the way the Earth should look at the COAS.
Thank you.
And thank you.
This was a really complex problem because without the benefit of automated systems, it was a three-man job.
Because it was a manual burn, we had a three-man operation. Jack would take care of the time. He'd tell us when to light off the engine, when to stop it. Fred handled pitch maneuver, I handled the roll maneuver, and I pushed the buttons to start and stop the engine. So maybe we ought to recommend a three-man LEM after this, I don't know.
That kind of maneuver takes an immense amount of skill, and this is where the selection of test pilots for the astronaut teams became really important. Here were people who were used to jobs in which their lives depended on making very precise, good, snap decisions, controlling aircraft in often very precarious situations. And so the Apollo 13 pilots were absolutely the right people to undertake this maneuver.
Okay, stand by. 2, 1, mark it.
Ignition.
Coordinating that maneuver between the three pilots was something that had to be done right first time.
Thrust looks good. Shut down.
And it's that test pilot background that really gave them that ability.
Okay, looks good. Nice work.
Let's hope it was.
Despite being cold and tired, the three astronauts execute yet another perfect burn maneuver, correcting the flight path and the critical re-entry angle.
How's it going, Fred?
It's fine.
Just wanted to let you know that you're pretty much right in the middle of the fairway there. And well, everybody down here is 100% optimistic. Looks like we're on the upside of the whole thing now.
Okay, that sounds good.
Jim, we're ready to put that battery back on the line.
So you want us to put battery 2 back on. Is that affirm?
That's affirm.
Okay, it's coming out. Bat 2's on the line.
Within hours of the oxygen tank rupture, Apollo 13's main power supply was dead. Without oxygen, the service module's 3 fuel cells could not generate electricity. But before the crew could evacuate to the lunar module, the command module systems started draining power from its precious re-entry batteries. This limited supply is the only power available for the capsule during re-entry.
The importance of the command module batteries is that you separate off the service module from the command module before you get to re-entry. And at that point, you lose all your power from the fuel cells. So you have to have batteries in the command module to keep you going, and the re-entry batteries do that job. And without them, you can't operate the command module through re-entry.
There was no way that the astronauts would survive if the re-entry batteries on the command module had less than full charge.
It has now been 3 days since the oxygen tank failure, and with Mission Control gearing up for the spacecraft's re-entry, their first concern is somehow recharging the command module's depleted batteries.
With no fuel cells on board to charge those batteries up, there was only one other solution, and that was to use the batteries in the lunar module to top up the batteries in the command module.
Basically a trickle charge, where you just keep it bleeding away while you're also using the main power of the lunar module to keep the main environment alive until you cut loose and you're just in the command module.
During preparations for Apollo 10, the mission control team had faced a training simulation, which also required the lunar module to recharge the re-entry batteries. Now, thanks to NASA's rigorous training program, ground engineers already have a proven procedure for battery charging at the ready. And having shortened the flight time earlier in the mission, there is definitely sufficient power in the command module to keep the crew alive and supply enough charge to the command module batteries.
We have a procedure which involves power transfer from the LEM to the CSM.
Okay, Houston, Aquarius, so we go for proceeding with battery charge.
Okay, go on the battery charge.
Roger.
The crew at this point has successfully completed the transfer of power from the LEM onto the command module battery charger, which is charging the 3 entry batteries to bring this from its current level of 20 amp hours up to about 40 amp hours, which would be essentially a full charge.
Our flight progressed that way down to about 5 hours prior to entering the atmosphere. And we were just merely hanging on. We had a dead service module. We had a command module that had no power to it. We had a lunar module that was a wonderful vehicle to travel home with, but didn't have a heat shield, unfortunately, and shortly we'd have to abandon it.
In preparation for re-entry, the service module is jettisoned, giving the crew their first chance to see the extensive damage to their crippled spacecraft.
You can jettison the service module when you're ready, no big rush. Okay, sounds good.
Jim and Fred were in the LEM, and when Jim yelled fire, I jettisoned the service module. And it went off, and Jim began to pitch around to try and photograph it.
It was, to me, sort of an amazing sight.
And there's one whole side of that street missing. Is that right? Right by the high gate antenna, the whole panel is blown out. Almost from the base to the engine. Copy that.
I couldn't see exactly what was damaged. I could see material hanging out from the interior, and Fred was taking pictures and Jack was taking pictures of the service module, trying to capture some of the damage that we could see.
With the dead service module set adrift in space, Mission Control and the crew turned their attention to powering up the frozen command module capsule.
The ground, of course, was working feverishly with Jack in the command module to make a successful entry through the atmosphere.
Aquarius, Houston. Go ahead. Okay, your go to start powering up the command module. Right-o, we're starting now.
Mission Control have developed an entirely new procedure for powering up the command module from scratch, something NASA never believed it would have to do while the capsule was in space.
The procedure in the command module was quite lengthy because we really threw away the book. We had never powered down a command module in space, and we had never reactivated one. And we wanted to get it right, and so I read back every switch and every circuit breaker.
But with an already limited power budget and time frame, this procedure is further complicated by the freezing temperatures on board the spacecraft.
They were breathing out water vapor. This was just condensing on the walls, running down the walls and windows. So there was a real concern about the moisture.
If things had not been insulated well and sealed, it would have gone into the electrics and could have caused short circuits. They probably wouldn't have got back.
The crew of Apollo 13 will now owe their lives to the lessons NASA learned from the Apollo 1 fire, when 3 astronauts were tragically killed in a test command module.
The Apollo 1 was an incredible tragedy for NASA, and obviously for the families involved. But it kind of brought NASA up to a halt. You know, it was just at the beginning of this program, and they'd lost 3 astronauts. That was a terrible shock.
The Apollo 1 fire was caused basically by bad quality workmanship in the wiring and NASA's lack of understanding of what it meant to pressurize the command module well above atmospheric pressure with pure oxygen. As soon as you do that, the flammability of materials increases tremendously and things burn so rapidly.
When a wire in one of the capsule's electrical systems arced, flammable material in the pure oxygen environment caught fire immediately, killing the crew in seconds.
So NASA learned a lot of lessons from that about switches, about wiring, about inflammable equipment.
There was a materials review all through the space program to make sure that anything in an oxygen atmosphere in a cabin was non-flammable. The funny thing is, they didn't look inside the oxygen tanks, and they were 100% oxygen with flammable materials in them, and that, of course, was one of the causes of the problems we had on Apollo 13.
But thanks to the insulation improvements made to the command module after the Apollo 1 disaster, condensed water in the Apollo 13 capsule environment will not short out any vital re-entry systems during the power-up.
I think they did an amazing job to get it powered up, considering it had been practically frozen for quite a long time.
I guess I really wasn't thinking along those lines because I knew that we were re-entering very shortly and that regardless of the damage to the heat shield, that you had to take it or not take it.
After the Apollo 13 mission, a review board was set up by NASA to investigate the cause of the oxygen tank failure. And it was eventually determined that an unlikely chain of events had resulted in a fire in oxygen tank number 2, causing it to rupture. But during the Apollo 13 mission, neither the crew or NASA had any firm ideas about what could have caused such a catastrophic system failure. Many at Mission Control had expressed their concerns about the integrity of the command module's re-entry heat shield. If there had been an explosion or meteor impact on board, shrapnel and debris may have cracked this vital protection against the intense heat of re-entry. And without an intact heat shield, the capsule and crew would burn up in the atmosphere. NASA has achieved the impossible. They have worked tirelessly and returned the stranded crew from the edge of disaster all the way back home to Earth. But Mission Control can do no more. Now all that stands between life and death for the crew is the hope that the command module's heat shield is intact.
My only thought then was, as I was sitting by myself inside the lunar module, I could see the Earth because it was the nice big triangular window. Well, Fred and Jack were powering up the command module, and even though maybe it wasn't noticeable to me, it looked like it was getting bigger and bigger and bigger. And I kept yelling back to Jack, "How are you coming? Are you doing fine? You know, when can I leave Aquarius?" Yeah.
He was a little bit nervous when he kept asking. He kept saying, "Jack, how you coming? The Earth is getting bigger." I think he was trying to hurry me, but I don't know.
But Jack did a fine job, which was, I think, accountable for some of our good guidance into a landing. I then went from the lunar module, closed the hatch, came on down, and we jettisoned the lunar module and came on in with a spacecraft.
With just 1 hour before re-entry, the crew must abandon the lunar module, the vehicle that has acted as a lifeboat for the last 4 days, and save their lives. The trials of the Apollo 13 mission remain a testament to the flexibility and reliability of the Apollo lunar module.
Okay, you are go for fire alarm. 305. I'm good. Okay, copy that. Farewell, Aquarius. Okay, thank you.
This is Apollo Control Houston at 141 hours, 31 minutes into the flight. We've had lunar module jettison. Apollo 13, the age of Aquarius ended at 141 hours, 30 minutes, ground elapsed time.
Well, I'm very much disappointed, just as Fred is and Jack, that we couldn't complete the mission. Marlow has so much to offer, we thought. We spent an awful lot of time on it. I, of course, would like to have landed on the moon, but I feel that perhaps what we got out of this flight was also well worth it.
The command module now plunges into Earth's thick atmosphere, losing radio contact with mission control. If they can survive re-entry, the astronauts will finally be home.
Apollo Control Houston, the period of blackout for the spacecraft should have begun about 20 some odd seconds ago. Apollo 13 should be coming up on max G right now. We have about 1 minute to go now from time of end to blackout. Continuing to monitor this Apollo Control Houston. Apollo 13 should be out of blackout at this time. We're standing by for any reports of acquisition.
Odyssey Houston, standing by, over. Odyssey Houston, standing by, over. Odyssey Houston, standing by, over.
Okay, go.
Roger that. Odyssey Houston, we show you on the mains. It really looks great.
Extremely loud applause as Apollo 13 on main chutes comes through loud and clear on the television display here.
Roger. Recovery on Blueberry 1. Apollo 13. Apollo 13. This is recovery, and your chutes look good.
The floor of the Mission Operations Control Room now crowded, and there are visible smiles on the faces of the flight controllers and astronauts in this room.
O Lord, we joyfully welcome back to Earth astronauts Lovell, Hayes, and Swigert, who, by your grace, their skill, and the skill of many men, return to us safe and whole. Amen.
kind of think one of the most important points that can be made of this flight is the cooperation and the coordination and the initiative that people have when suddenly faced with an unusual situation that can respond to come up with the answers. And they did. They read us up procedures. Fred, Jack, and I practiced these procedures by reading them and then completed them. I think it's amazing the way that people can respond so fast to get this job done.
You know, there's a saying about a steely-eyed missile man, about people who work on rockets and spacecraft. And that accolade is only given to a very cherished few who have that quality, what you might call the right stuff. It was not until all those 3 parachutes came out and you saw splashdown that then all those emotions were released.
Personally, I regard Apollo 13 as an immensely impressive example of engineering. The systems engineering, the organizational engineering was so solid, was so intelligent, was so well structured that when the accident happened, the organization was found totally capable of dealing with it. And I think that's very impressive, and I can't imagine why anybody would want to be anything other than an engineer.
It was certainly an amazing achievement. Obviously, we were really over the moon that we got them back.
I think Apollo 13 did show NASA and engineering their very best, and it's a matter of pride to have worked on the Apollo program.
Being able to take a crew of 3 astronauts in a severely wounded ship, bring it around the moon to a safe landing back on Earth using techniques which in many cases hadn't been thought of until that moment in time is a remarkable achievement. I think Apollo 13 is possibly the pinnacle of NASA's achievements in space so far.
Failure is not an option. And it was that idea that we could prevail, that we had to respect the science, the physics, and the engineering, never let it get away from us, but we can do these things. It was the finest example of that spirit that's not only in NASA, it's within people, this is humans that did this. In this situation, and all similar situations, it's really about people and about what they give beyond what they're asked for.